Are you ready to rock? The last problem. No, I promise. Boy Scouts honor. Sorry. I changed my shirt. You notice? That's because this problem is intense. This problem is like camping. Okay, like camping. It's intense. Like camp. Okay, sorry. Let's get going. Last one. Whew, I'm ready. Now I'm ready. Okay. Calorimetry, last problem. It says a piece of aluminum, 100 degrees, so it's like super duper hot, is going to be placed into a calorimeter. Now, a calorimeter is just something that doesn't let heat in or out of the system. I mean, it can be as simple as a Dunkin' Donuts styrofoam cup, which they don't have anymore, which is good. And thank you, Dunkin' Donuts, for doing that. But a styrofoam cup is a good calorimeter. It doesn't let heat in or out. So we are going to, we would use more sophisticated calorimeters, but whatever. We're not going to be able to do that now, are we? Okay, so a calorimeter, you put something in it, doesn't let heat in or out, and you can just assess what happens within the system of the calorimeter. Okay, we're putting this hot metal into 500 milliliters of water, which we all remember is 500 grams. A milliliter of water equals a gram of water. At 20 degrees Celsius, nice room temperature water. What's the final temperature of the mixture? Final temperature of the mixture. Well, heat is equal to M delta T C E. All right, that is the Pacific heat capacity as opposed to the Atlantic heat capacity. It's funny, it's an ocean joke. Get it? Ah, it's funny. Now, we need to figure out what the final temperature of the mixture is. You have a mixture of hot water. Yeah, no, strike that, reverse. Cold water, hot metal. So here's your calorimeter, got some sweet, sweet water in there. It's hanging out, chilling like a villain. Yo, what water does, you take this piece of metal and you go kaplop, put it in there. Well, what's gonna happen to the metal? It's gotta get cooler. And what's gonna happen to the temperature of the water? It's gotta get warmer. So in between, the east is east, the west is west, and never the twain shall meet. I think I wrote that. Yeah, that was me. No, actually it wasn't me. But the point is, you're going to have metal and water, different temperatures, they'll converge to some point where they have what's called an equilibrium temperature, where they both settle on some temperature. Now, you all know what Pacific heat capacity is. You know it has something to do with the ability of an object or material to absorb heat energy. And we've learned that water has a very high specific heat. Now what that means is water is like Keanu Reeves in the movie The Matrix. Bring it. You got nothing. Bring it. That's what water says. Water says you ain't got nothing. You can put stuff into water and it takes a lot of heat energy to make water get warmer. It doesn't change very much, which is again why it's used as a coolant in things like automobiles. Absorbs a lot of heat energy. So the water is going to absorb a lot of the energy. The metal, what have we learned? Metals have a lower specific capacity, which means they can change their temperatures very rapidly. So the aluminum will very quickly give its heat temperature to the water. The water will laugh at the metal, saying you ain't got nothing. So the water temperature should not go up that much. So we suspect when we calculate this, we should get a temperature that's much closer to the temperature of the water than that of the metal. All right, now, so how do we do this problem? Well, one thing's loss is another thing's gain. That's the way it is in life, and that's the way it is in chemistry, which is, we all know, life. So if something is losing heat, something else must be getting the heat. So let's set the equation, the heat equation, equal to itself, because one thing's temperature heat loss is the other thing's temperature heat gain. So we set up Q loss equal Q gain. You knew that. So if I put the equation in for Q, pretty sweet. Oh, well, things on both sides are the same, so we can cancel out the masses and the specific heat capacities and the change in temperatures, cancel all them out, problem solved. But no, because these are different masses. They're not the same material, different specific heat. So we got water and copper, and no lies aluminum, and so we and they're going to have different temperature changes. So no, we can't just cancel everything out. Okay, thought you can get away with it too. You would have if it wasn't those meddling kids. Okay, so the mass. Now, who's losing Who's losing heat here? Come on, you know, you can say it. Very good, Michael. You know that it's going to be the metal. Hot loses, cold gains. So here, the aluminum and the water. What is the gainer? The aluminum's a loser, such a loser, yeah. So we are going to put in the information for aluminum on the left and for water on the right. Let's go ahead and do it. Do it, yeah. All right, aluminum, how much did we have? We had 300 gram piece of aluminum. So 300. Temperature change of the aluminum. Okay,